Hello, everyone, and welcome back. In the previous video, we introduced some properties of continuous functions. And in particular, we introduced one of the properties that you are probably familiar with, and that is the intermediate value theorem. Now, in an introductory calculus class, you typically are met with three major theorems about continuous or differentiable functions. That is the intermediate value theorem. The last one is typically the mean value theorem, which is something we'll get to, but we need derivatives to get there, so we can't do that right away. But the other one that you learn is the extreme value theorem. And that's going to be the focal point of today's lecture. We are going to state and prove the extreme value theorem, and then show, some examples, how we can use it, and we can talk about some properties of continuous functions based on the extreme value theorem. So let's go ahead. Let's get right into it. Let's have a little bit of fun talking about continuous functions again today. So what we want to do is first start with a definition. We always start with definitions, right? So here's our definition that we're going to start with today. We say a function f is bounded on a domain D, provided there exists little m and big M in R, such that little m is less than or equal to f of x, which is greater than or equal, or is less than or equal to capital M for all x in your domain. Okay, so let's make this red so that we can emphasize it. And let's just think about this for a second. This is a fairly intuitive thing for you to think about. You can draw two vertical lines in the XY plane, and your function is entirely in between those two vertical lines, right? So your bottom one is little m, your top one is capital M, and your function is doing everything it wants, but only within that little or that infinite rectangle. Now, of course, not all functions are bounded. There are plenty of functions we can find that are not bounded. For example, just f of x equal to x over the real numbers, not bounded. Or, 1 over x, again, not bounded. It's got asymptotes at 0. But there are plenty of functions that are bounded, even over the entire real numbers. For example, e to the minus x squared, your typical little bell curve function, that thing is between 0 and 1 for every single value of x. Now, what we're going to focus on today is functions primarily restricted to closed intervals. Now, we saw in the previous lecture that closed intervals are important, right? It says that continuity of a function on a closed interval is also uniform continuity. Very, very powerful result, right? It tells us a lot more about the behavior of the function. Well, we get something similar in this case. So we have the following theorem. If f is continuous on a closed interval a to b, then f is bounded on a to b. So for example, if you have f of x is equal to x and you put that on the interval 0 to 1, it's bounded on that interval, right? So a lot of people think about functions independently of the domain. If I say f of x equal to x, you say, well, that thing's not bounded, right? And that's an old way of thinking. You should always be thinking about functions as a pairing. It is not just the definition of the function, but the domain where you're allowed to pick your x's from. So, saying this function f of x equal to x on 0, 1 is very, very different than saying this function, right? They look like the same function. It's the same definition. It's the same sort of intuition that we can use to analyze it. But what's different here is the domains that these things are allowed to be picked from. And you should always, going forward, think about a function in terms of its domain. If somebody gives you a function, you say, well, what's the domain? You need to tell me. You need to specify this for me. Okay, so let's take a look at the proof here. The proof is, it's kind of fun because it uses that uniform continuity, right? So we know that f in the continuous functions on a closed interval implies f is uniformly continuous on AB. We proved that. That was the last thing that we proved in the previous lecture. So thus, if we pick, remember, uniform continuity says for all epsilon greater than 0. Well, what I want to do is I want to pick an epsilon bigger than 0. In my case, why choose any number but 1? Easiest positive number to work with, in my opinion. Mathematicians, I joke that we only have 2 numbers that we care about, 0 and 1. I know that's not true, but it's sort of typical of an analysis class like this. And then there exists a delta greater than 0 such that for all x1 and x2 in the domain, such that they are within delta of each other, this implies that f of x1 minus f of x2 is less than 1, right? That's my value of epsilon in this case. So I substituted epsilon for 1. So now consider the sequence. So we're going to sort of discretize the domain, sequence of evenly spaced points. As follows. So we're going to say let x1 be the left endpoint. x2 is going to be going delta forward from that left endpoint. x3 is going to be going 2 delta forward from that left endpoint. x4 is equal to 4 delta or 3 deltas forward, and so on and so forth. And of course, by the Archimedean property, we have to eventually cover this whole domain. So then there exists, some terminal point. So let's go all the way up to some capital N such that x sub capital N is equal to B. Now, if you're familiar with Riemann integrals, this is sort of what you do with a Riemann integral, right? You sort of evenly space out your domain and you divide it up into little points and you sample the function at those points. Again, moving delta across this domain, because it has finite length, b minus a, well, the Archimedean property tells you that if you add enough deltas together, you're eventually going to stretch over the domain. So you're going to call that capital N comes from the Archimedean property. You're going to call x capital N the last element of the domain. So then we're going to use uniform continuity here. Well, if you look at x between, say, x1 and x2, this implies, okay, so again, f of x1 minus f of x2 is less than 1 because of uniform continuity. If I disentangle that absolute value, so I make -1 is less than f of x1 minus f of x2, which is less than 1, and I sort of rearrange a little bit. This is equivalent to saying that f of x1 minus 1 is less than every f of x in that interval, which is less than f of x1 plus 1. So all I did was took the definition of uniform continuity, opened up the absolute value, and moved things around a little bit. Similarly, if I take x between x2 and x3, again, the length of these intervals is delta, so the uniform continuity properties apply. I get f of x2 is less than f of x, which is less than f of x2 plus 1. And you can keep going. And then you go all the way down to xn minus 1 to xn. And I want to remind you, I just put this in green. This thing is the left end or the right endpoint B. So you stretch the whole domain now. Well, you get f of xn minus 1, which is less than f of x, which is less than f of xn minus 1 plus 1. But then what have you done? You have taken every single value in the domain, f of x, and you have bounded it depending on where you are in this little discrete collection of intervals that you've broken your domain up into. And there's only finitely many intervals, right? There's capital N of them. Actually, there's capital N minus 1 of them. But then this tells me that I can say, if we let little m equal to f of x1 minus 1, f of x2 minus 1, all the way up to f of xn minus 1 minus 1. And if we let capital M, sorry, this should be the minimum, pardon me, m equal to the minimum. So the minimum over capital N minus 1 terms, there's only finitely many of them, so there's got to be a smallest element. And similarly, you take the maximum here of all of those, but with a plus 1. Well, from what I had on the previous page, I have bounded, I've got upper and lower bounds on every value of f of x, right? So if I take a look at what I have here, I've got f of x bounded in every single case. And that tells us then for all x in AB, we have m is less than or equal to f of x, which is less than or equal to m, which implies f is bounded. And again, that just comes from uniform continuity, right? That's all that was. Again, you need a closed interval to make this work. In our case, we needed a closed interval because we used uniform continuity. We needed to guarantee we had that. But it's pretty easy to see. There's many counterexamples that you could come up with that show you why you need a closed interval here, right? If I take f of x equal to x on the open interval 0 to 1, in that case, you know, you're not going to be bounded, or there's not going to be a smallest value and there's not going to be a largest value. And that leads naturally to our next definition here. So our definition says, we say f has a maximum value we'll call this capital M again. M stands for maximum, capital M at least, on a domain D, provided there exists x capital M in the domain such that f of x is less than or equal to f of x sub m, which is equal to your maximal value m, and that's for all x in the domain, right? So whatever you plug in x capital M, you get a bigger value at f than you would for anything else. Similarly, you can probably guess where this is going. We say f has a minimum value, and I don't want this to be too confusing, but I'm going to use little m. Again, max and min start with the same letter, so we use little m because it's smaller in some sense, you know, sort of conceptually, on D, provided there exists x little m in D. Now, I know that the x capital M and x little m sort of look alike. I'm making my little m's rounded and my capital M's very jagged and sharp so that we can disambiguate these. Such that if I take any other point in the domain, this is going to be greater than or equal to my x sub m, and this is again for all x in D. Okay, so this tells you that you have a maximum or a minimum value for your function f. And you might be familiar with this, but the next theorem leads naturally to telling you when you have exactly max and min values. And this is referred to as the extreme value theorem. So again, you may be familiar with this theorem, especially if you took an introductory calculus class. You probably used it along with the intermediate value theorem, and as I mentioned, maybe with the mean value theorem. So let's say if f is a continuous function on the closed interval a to b. Again, we're always using the closed interval. In the next lecture, we're going to talk a lot about the space of continuous functions on closed intervals. We'll see it has a lot of nice properties. Well, then f has both a maximum and a minimum value on that interval a to b. Okay, so that's the extreme value theorem, right? It says that if you have a continuous function on a closed interval, then there's some maximum that it hits and there's some minimum that it also hits. Okay. So the proof of this, it's actually quite nice. It's going to use the Bolzano-Weierstrass theorem, which is very exciting. We love using the Bolzano-Weierstrass theorem. It's one of the most powerful theorems in all of analysis. So we know that this thing is bounded. So by the previous theorem, we know I'm going to put this in bracket or in quotations, the range. We haven't defined it, but again, you probably know what this means. We know the range, which if you don't know what it means, here's the definition. It's the set of all of the values that f of x can take, given you take something from the domain. Of course, this is not the empty set because I can always just plug something in here. We know this thing is bounded, right? It has a maximal and minimal bound from above and below, both above and below. And below. Well, this is a set, and therefore it has a least upper bound. So let's say let capital M equal to the supremum of this thing. So you're saying, well, the range is bounded above, so therefore we know that it has a least upper bound, and let's call this thing capital M. And I'm going to only prove this for the upper bound. You can see the lower bound follows in exactly the same way. So you can repeat the arguments yourself and sort of fill in the blanks. It's a nice exercise. So this says, hence, for all k in the natural numbers, m minus 1 over k is too small to be an upper bound, right? So this is just the definition of the least upper bound, which is coming by proxy of the supremum. So there exists xk in AB such that, now let me move to the next page, but this says that if you try to make an upper bound of m minus k, well, this is clearly smaller than f of xk. That is the point of the supremum. You can always find, if it's not an upper bound, then there's something in the set that gives you something bigger. And so this is by definition less than or equal to m. Well, since x sub k belongs to AB, so this is going to look a lot like what we did in the previous lecture for uniform continuity. This implies xk is bounded, right? It has an upper bound of B, a lower bound of A. And so the Bolzano-Weierstrass theorem, so the same thing that we did for the proof of uniform continuity in the previous lecture, implies there exists a subsequence, let's call it x sub kj. J is the next letter in the alphabet. That's why I'm using it. Converging to some, I'm going to call this x sub capital M because you know what it's going to be. It's going to be that value that I'm looking for as j goes to infinity. And I'm switching up the indices here because I want you to see that, indices don't matter. I don't have to use x sub n and x sub nk. I can use x sub k and x sub kj. So, but what happens here? Well, m minus 1 over kj is less than f of x, sorry, kj, I'm confusing myself now. Kj, which is less than or equal to m by definition. And kj goes to infinity as j goes to infinity. That's just from the definition of the subsequence. So m minus 1 over kj goes to m as j goes to infinity. So the lower bound is coming up, and f of xkj approaches, well, actually, let's write it all out. We have m minus 1 over kj, which is less than f of xkj, which is less than or equal to m. Let's draw this out in terms of all of the convergence here. This is converging to m as j goes to infinity here. Clearly, the upper bound is just constant. And so also this thing is continuous, f is continuous. So this is approaching f of x sub m. And the inequalities are preserved in the limit. And so therefore, by the squeeze theorem, f of x sub m is equal to m. All right, so we didn't prove the squeeze theorem in this lecture series, but again, you don't really need it. You can kind of see it at work here. You're just sort of coming up from below and you're sort of crushing yourself into that upper bound. So the existence of a lower, or this is, so x sub m is a maximum value. The existence, so I'm just going to write a little note here of a minimum value follows in the same way. Okay, so I'm not going to prove it. I want you to try and tackle it on your own to make sure that you understand how to sort of replicate this proof or modify it in such a way that you can find a minimum value. But nonetheless, that's the extreme value theorem. Now, let me give you an example here. And this example is going to throw you a curveball. So let's go to a whole new page. This is going to be a little bit of writing. But let's say let p of x be a polynomial x squared minus x plus 1. And because we have a function, we also need a domain. So we're going to go over all real numbers. So immediately you think, Jason, why, right? You just gave me the extreme value theorem. Clearly, you're going to ask me something about minimum and maximum values of this thing, but it's not on a closed interval. So why, right? Well, we claim P, now this thing must have a minimum value on R. Okay, so this thing doesn't have a maximum value. You know quadratic functions, right? They open, in this case, you have a positive leading value. It's opening up. And so it's not going to have a maximum value on R. But you also know quadratic functions. There's a turnaround point, the vertex at the bottom. And so that's its minimum. We're going to prove that this thing actually has a minimum. And the issue, as I said, is you cannot apply the extreme value theorem here because the real numbers are not a closed interval. So that's not going to work. So how are we going to do this? Well, we're going to be super clever. First, let's consider, let's take p of x and let's factor in x squared out of every term. I get 1 minus 1 over x plus 1 over x squared. Okay, so I have two factors. Now, note 1 minus 1 over x plus 1 over x squared. This thing converges to 0 as x goes to plus or minus infinity. Right? You don't need too much machinery to do that. You can use a lot of our understanding of the previous from the previous lectures. So that's true. Thus, that tells us that there exists some capital M such that if you look at x outside of that region of M, then this implies that this implies that 1 minus 1 over x plus 1 over x squared is greater than 1/2. Sorry, I made a mistake here. This thing doesn't go to 0, it goes to 1, right? You probably caught it. You saw my mistake, and that's why things were not making sense here. But of course, 1 over x goes to 0, 1 over x squared goes to 0. That leaves you with just the 1. And so that means that if you're going to approach 1, eventually everything's got to be bigger than 1/2, right? This is just a limit argument. You can do this with sequences. We do this all the time. So that means that if you look on the number line outside of some minus m to m interval, everything is at 1/2, right? And that comes from the fact that as you go to plus or minus infinity on this thing, you're getting very, very close to 1. That's fine, right? We can do that. Now also observe that p of 0 is equal to 1. That's easy to see. And if the absolute value of x is bigger than the square root of 2, then x squared is bigger than 2. Again, that's pretty simple. You should be able to follow that, I hope. So hence, if we choose a equal to the maximum of the square root of 2 and capital M, then if we look outside of this interval, so if we look at x larger than a, well, because x is larger than or equal to the square root of 2, x squared is bigger than 2. And because x is going to be larger than or equal to capital M, the second factor in our p of x expression, so that is this piece right here, is bigger than 1/2. So that tells us that this implies that p of x is greater than 1, right? 2 times 1/2, which is equal to p of 0. So, as long as we look outside of that interval, we have bigger values than p of 0. Okay, so now that means that everything outside the interval is bigger than some point we've already identified. That means we can just restrict ourselves to the smaller interval, minus a to a. So now p belongs to the continuous interval minus, or the set of continuous functions from minus a to a, right? It's a polynomial. It's continuous on any domain that we give it. And so now we've got a closed interval. So now the extreme value theorem it guarantees us, I think I spelled that wrong, just a second. Guarantees. Okay, it guarantees that there exists an x little m, so it's curved. Sorry if it's hard to distinguish from a capital M. In this case, it won't make much of a difference. But that tells us such that p of x little m is less than or equal to p of x for all x in minus a to a. But you know what's in minus a to a? 0. So, but this implies that p of x sub m is less than or equal to p of 0. Again, that comes from the extreme value theorem, which is equal to 1, which is less than or equal to p of x for all x outside of that interval. Therefore, it works for all x inside the interval. It works for all x outside the interval. Therefore, p of x little m is less than or equal to p of x for all x in R, which implies p has a minimum value. So that was a cool application, right? We sort of had to go down the rabbit hole a little bit. We had to do a lot of thinking with this and figuring out, how we can actually apply the mean value theorem. And the basic premise of this, if you sort of take the long view, if you sort of zoom out a little bit without looking at the analysis is on the page, you know that quadratic functions open up in this case because it has a positive value. It opens up. And so that means that if you look far enough out in X, everything is going to be big. Everything is big. So it'd say, okay, I don't care from minus 100 to 100. If you go bigger or smaller than 100 or minus 100, you know what I mean, outside of that interval, things are too big. Clearly, the minimum's not in there. So then what you do is you restrict yourself to that closed interval, minus 100 to positive 100. You apply the extreme value theorem and you say, well, everything outside of that was already too big. And so I found a minimum in the closed interval, and therefore it's a minimum over the whole thing. That's basically the process here. Now, of course, we did it with analysis. We made it much more rigorous than what I just said there, but it's all there. Okay, let's finish up with one nice little theorem. And this says, if we have a continuous function on AB, so this is just like a natural extension of the extreme value theorem. So then the range, again, remember I introduced, or I sort of alluded to it, you're probably familiar with it. It's just the set of all values that f can take given x is in the domain. So I'm going to put it in red because it's sort of being highlighted. Maybe it's something to look into. So then the range of f is a closed finite interval. Okay, so what does that say? That says if you look at a continuous function on a closed interval, then its image is also going to be a closed interval. That's pretty cool, right? It sort of says take a closed interval and you get a closed interval. And the proof of this is basically just evoking the extreme value theorem. So recall the range of f is, now we have a way of denoting this. It's f evaluated at the interval, right? So this means f at every single point. Now, this is just sort of notation that mathematicians use. It's not supposed to be sort of taken literally, but this just means the set of all f of x's such that x came from the domain. So you imagine, you're going to put x's into this thing, just put all of them in right away. That's all that notation is telling you. So since f achieves a maximum value, value of capital M and a minimum value of little m, the intermediate value theorem, so the previous piece, the existence of a maximum and a minimum comes from the extreme value theorem. Here now we're wrapping it up with the intermediate value theorem. This thing assures us that f achieves every value between little m and capital M. Hence, the range, remember we have this shorthand notation, it stretches all the way from little m up to capital M. And therefore, it's an interval. I can get every single thing in there, right? I might get everything twice, but who cares, right? I still got it. That's the fact. That's what matters, is that, I got everything between little m and capital M, and I got it inclusively because I know that I have to achieve the maximum and minimum values by the extreme value theorem. Okay, so that's all we have for this lecture. What we introduced is the extreme value theorem, the concept that, continuous functions on a closed interval achieve maxima and minima. And what we got to do is we got to play with a nice little example and see how we can actually use this for maybe functions that don't necessarily fit into the mold of the extreme value theorem. Now, you can repeat that argument that I used for that specific polynomial to show that all quadratic polynomials with positive leading coefficient has a minimum. And if it has a negative leading coefficient, then it has a maximum. You can repeat all of these ideas. You could even repeat that idea for all even degree polynomials. So x to the 4 plus a bunch of stuff, x to the 6 plus a bunch of stuff. So that's really the utility, right? The utility is that although the statement of the theorem is given in terms of very restrictive, continuous function on a closed interval, we can, work through specific problems and reduce them down to a place where we can apply these theorems, and then we can get really nice results based on them.